I did make a video, but unfortunately it just didn't record. Wait, it recorded and then it just didn't save. So it's quite frustrating when you're talking for probably 20, 30 minutes at once. So what I will do is I'm just going to go through my working here just to save me effort and time and my voice. And apologies, it's not as good as working it fresh, but I'll just talk it out. So we want to evaluate logarithms in this first example here. So we're thinking in blue, what's log of 100? Now, what's the base of log in 100? It's base 10. So if a log doesn't have the base shown, it's always 10. Now, the way to think of a log is 10 to the power of something is going to make this number here, which in this case is 100. Well, I know I have to times by 10 two times, so 10 squared, to make 100. So 10 squared is 100. Therefore, how many times do I have to times by 10 to make it 100? 2 times. And that's my answer. Let's move on to log 10 of 0.1. So we have to think, how many times do I have to multiply 10 to make 0.1? A little bit more abstract, so we can think of it like this. 10 to the power of something equals 0.1. And we know that this must be 10 to the negative 1. Remember from our table that all the decimal numbers we should know for the powers. Now, before we move on to this monstrosity over here, I want to have a think about what's another way of doing this, which I think is a more advanced way that may seem a little bit sort of bulky, not that intuitive at the start, but we can use it for more challenging problems like this. So instead of going 10 to the power of something makes 100, we can express this 100, as base 10. So we have to match these bases here. 10 squared makes 100. And then if you've got a base 10 and the base 10 the logarithm and the base 10 is here, then you can simply just respond by saying that the index is the answer, right? So 10 has to be to the 10 two times to make 100. So the index comes down here. Same thing, 0.1, match the bases, so 10, 10. 10 to the negative 1, the answer is negative 1. Using this principle, we're going to apply it to this problem over here. For your notes, how we call it is log base a to the x is equal to x, so that index just comes down. Now this rule is really useful. It's a little bit abstract, so it's really useful to have a general rule, and we need to be able to work both ways on it. Sometimes we're working this way to go this way, and sometimes we have like a number and we need to convert back into log form, which we do later. Let's tackle this one here. So log the fourth root of 100,000. First thing is let's try to make this match the base. Well, the base is 10 of the log, therefore we need to make this number base 10 as well. So 10 to the power of something. Now this is going to be 100,000 to the power of a quarter, because it's the same as the fourth root. Next step, let's express this as the base 10, so 10 to the 5, 1, 2, 3, 4, 5. Then we times the indices together. Do you remember, it's like the fourth or fifth index rule. 5 on 4. Now that we match the 10s, the 5 and 4 comes down. Okay. Now this is a nice introduction into how logs work and also how to think about them. Let's change the base up now and let's look at some logs of different bases. In this case here, we've got log base 3 of 81, log base 4 of 1 on 64, and log base 36 of 6. Now in this one here, we use exactly the same rule. Log base 3, so match the 3. 3 to the power of something makes 81. 3 to the power of 4 makes 81. Then your 4 comes down here. Over here, log base 4 of 1 on 64 is the same as log base 4 of 1 on 4 to the 3. Make it a numerator, so log base 4, 4 to the negative 3, and our answer is the index, negative 3. In the last one, and this gets lots of people, it's log base 36 of 6, match the base. Log base 36 of 36 to the something. Most people freak out on this one, but if I go 36 to the half, I know it's the same as saying the square root of 36. Therefore, our answer for this one is a half. Now, you'd find these questions in the non-calc part of a test, as you can see, and you have to be pretty handy with the old index rules and knowing your powers to do all these effectively. We're going to move on now to the log laws. Now, the log laws represent some very, like the index laws, but as you can see, there's nowhere near as many log laws as there are index laws. The first one is log base a m plus log base a n. We can basically express this as a single logarithm of the same base by timesing the numbers inside the log here, so m times n. Similarly, if there's a take here, this converts to a divide, very similar. And the last one is log base a m to the n. The n can become the coefficient of this same thing. So you can think of the n going to the front of this, or the n, the coefficient, becoming a power instead. Now, this is what logs do really well, is they bring a power and make it a numerator so we can solve for them. Okay? Now, we're going to work on these problems here, and these are classic problems. In purple was the original question. So the first one was 3ln2 plus half ln 64. Now we want to simplify these. Now simplify means express as a single simplified logarithm. We can see here that it's not a single logarithm, and we want to merge them together. The first step is no coefficients, and we want to match the log bases, right? Now we can see here that it doesn't say log, it says ln. Now ln represents the natural logarithm. The natural logarithm is related to the natural exponential, which we know is 2.7183 yada yada, which is an irrational number. It's a very special number because it comes out of nature and it represents a continuous change or continuous growth. And we can't really be bothered writing log e all the time, so instead we write ln, but you can think of ln as a log with base e. Now this example I really like is if you're asked to find what's ln e to the 3, you go, I'm not sure. But if you remember it being log base e, we can see this rule coming into play again, this one here. If you match the bases, the index is the answer. Oh, we have e to the e, therefore 3 is the answer. Really, really handy there because we can go now from 3 to ln e to the 3 if we want as well. So here we go. Let's look at this one. 3 ln2 plus half ln 64. First step, no coefficients. So bring the 3 up there and the half here. Now I know that 2 cubed is 8, so we're evaluating now, and the square root of 64 is 8. Next step is we want to bring these together, ln 8 plus ln 8. Now there's two ways of doing this. You can say there's 2 lots of ln 8 here, and then the 2 goes up to the 8. That's the third log law. Then it's ln of 64. Or in the purple here, we can use the first log law and bring these together. And remember, if you're adding 2 logs together of the same log, then 8 times 8, right? Which is 64. So they're both different ways of getting the same answer. Let's move on and do ln 5 take 3. Now, it's pretty common to have just a number by itself, but it's a little bit abstract having to convert this into the same base. So first step, get rid of this coefficient. 2 goes up to the 5, so it becomes 25, so 5 squared. Then the 3 needs to get converted into the same log. Now in this case, you're using ln, so this will also have to be expressed as ln. Now we remember from before that ln e to the 3 is equal to 3. So I can replace this with ln e to the 3. And remember that we know that this comes from this rule here, x is equal to ln e to the x, where the x is the index. The next step is, now that we've got it as the same log, we can simplify the simplify the log and express it as a single log. The second log law is if they're a take, then we can divide, and there's our answer. The last one over here is another one to practice. Log base 4, 2. I've gone straight to the answer here. 2 to the 5 is 32. And then 2 would be expressed as, well, it's a base 4, so we have to match the bases. So it'll be base 4, 4 squared. Let's evaluate these. 4 squared is 16, and then our answer will be log base 4 of first log law, 32 times by 16. So there we go. We've done some simplifying of logarithms, and this will all be found in the non-calc. We're next going to be looking at converting exponential between exponential and log equations. The first set of examples we're looking at is going from exponential to log equations. So we've got this function here, a is equal to p times b to the n. We can say this is an exponential function because there's a power. First step is we want to get this into a log, Now what we're going to do is we're going to take a log of both sides. So log of a and log of p times b to the n. The next step is we want to simplify these logs as much as we can, which means breaking them out into as many terms that represents each of the variables. So we have a p variable and a b variable. So let's see if we can break these apart. Well, remember our first rule, we're going to be working the other way now. So remember I said we have to work both ways. We have a something times a something, and then we can break that up and bring the m by itself here plus another log with the n by itself. So here we go. Log p plus log b of n. So we're just breaking up those terms. The next step is, when we're going into log equations, is we don't like any powers. Logs try to bring powers to a numerator. Therefore, this n goes to the coefficient of log b, as in log law 3. The next example is just a little bit more chaotic. Do the same steps. Take a log of both sides. Log c is equal to log of all this. Then we want to break this apart. So it's going to be log a squared plus log b to the 3n, take log k to the half. The next step is we want to get rid of all the coefficients. So they all go to the front, all the powers, and they become coefficients, so we put them at the front. And that's it done. In the next set of examples, we're going the other way. We're going from logs to exponential functions. So we can see here we have this ln r is equal to 2 ln t take half ln q. We want to express this as an exponential function again. The first step is get the left-hand side and the right-hand side as a single log that matches and have no coefficients, i.e. convert everything to powers. So we're working the other way as what we did before. First step is we can get rid of these coefficients. So 2 can go up to the t squared, and the half can go to the q to the half. The next step is now we can express as a single ln on both sides. So ln r, that stays the same, is equal to ln t squared divided by the square root of q, because this is a take, so it goes into divide, and the half goes into the square root. Now this is the strangest bit, is we can get rid of the ln functions by putting both sides to the e. So e to the power of something, as in this side, and e to the power of this side. Now we know that e to the power of ln, they undo each other. So we're just left simply with r and what's in this brackets here. So the answer is r is equal to t squared on root q. And that's our answer. Another way of looking at it is if these are the same, the natural logarithms, then the insides must equal. You can think about it either way. Let's have a look at this one over here. Log e is equal to log m plus 2 log c. We want to get the coefficients to the powers, so 2 goes here. So log e is equal to log m plus log c squared. Bring them together now, mc squared, and then go 10 to the power of everything, because it's log base 10, or just the insides of the logs are equal. So e is equal to mc squared, the old famous equation. We're now going to move on to something called the changing base rule and also solving some logarithmic equations. I've already made a video on logarithmic equations for 6G, but 6E also has some solving logarithmic equations too. So what I'm going to do is look through solving logarithmic equations, then do some changing base rules. The first step here is we've got these nice 5 steps on how to solve logarithmic equations. It's not meant for every single situation, but I find it's the order I do things in, and it's quite useful to think this way. The first thing is write all terms in log form with the same base. Now we can see here these all have the same base, so we can basically tick that one off already. 2 says simplify all logs so there's no coefficients. There's no coefficients here either. We're going really well. 3, simplify all logs so there's only one log term on the left-hand side and the right-hand side of the equation. Now we can work on this. So log base 4 of 64 times by 1 on 16. This side's already expressed as a single log of base 4. We can evaluate this. 64 times 1 on 16 becomes 4. And much like the exponential functions, if this log base 4 and log base 4 over here, then it stands to reason that the insides must be equal to. So 4 is equal to x plus 1, x must be equal to 3. Now, the last step here, it says discount values with a negative input into a log, i.e. log k must have a k value greater than 0. Now we can see here, if I got this 3 and put this into where the x is, log base 4, 3 plus 1 is 4, that is a possible value, so we're okay. Let's move on to B. So the first step, write all terms in log base form. We've already done that one. But step 2, simplify all logs. There's no coefficients. So here we go. The 2 goes to the x, so x squared, and we have no more there. We also want to match this log here. This is log base 10. So how do I make a 2 in log base 10 form? Well, it's log base 10 squared. Remember, this is base 10 when it's blank. Next step is we want to bring these together. So they become x squared on 4 is equal to log of 100. We now equate the insides. So it's x squared on 4 is equal to 100. Rearrange, times by 4 both sides. Take the square root plus and minus of 400. Then this is the interesting bit. Two answers come out. X is equal to negative 20 and 20. Now, we're actually not finished there. Do you remember step 5? So for logs, this is very important. Discount values with a negative input into a log. So you can see here that I've crossed out negative 20. Let's see why. If I put negative 20 here, you can see it's going to be log of negative 20. Now the problem is I can't have a log of a negative value. I'll show you why. Let's pretend we're looking at log base 10 of negative 100. How could I ever make negative 100? Well, 10 to the power of something makes negative 100. Can we think what that might be? A tempting thing to do is 10 to the negative 2, but 10 to the negative 2 doesn't make negative 100. It makes 1 and 100. It's impossible for 10 to the power of something to be negative 100. Therefore, we can't have a negative log like that. So we cross out that negative 20 answer. Now, I think it's a good idea to still write out both answers and just cross one out. It shows the marker you know what you're doing. Okay, so let's move on to this next one. These all have the same base 3. Therefore, we can times the insides to make a single logarithm. X times by x plus 2, is equal to log base 3 of 12. We can now equate the insides. X times x plus 2 is equal to 12. Now, this is going to be quadratic. If we expand this, it's x squared plus 2x, take 12, is going to be equal to 0. Now, I actually couldn't think of any numbers that times together to make negative 12 and add together to make 2. Therefore, I know that's probably not going to be a nice solution, as in it's not going to be whole numbers. It's probably going to be a square root solution. So I've used complete the square here, half the 2, then take the 1 to balance it, then bring the take 12 down. Then I've brought the 13 to this side, take a plus or minus square root of both sides. Now I've got two answers. Now do you remember what we said before? Discount negative logs. So we've got a negative log possibility here. X is equal to negative 1 plus or minus root 13. Now I know that root 13 is going to be above 3 squared, so it's going to be above 3, but it's going to be below 4 because that's 16. Therefore, it's going to be around, let's say, 3.5. The two possibilities I have is negative 1 plus 3.5, which is around 2.5. The other one is negative 1 take 3.5, which is negative 4.5. Now I can see I cannot have that negative answer. Therefore, the only answer I will accept is negative 1 plus root 13. So now we're going to move on to the change of base rule. Here we go. So I like to introduce it like this. In fact, we'll do that. If I want to break open log base 4 of 6, I can actually express this in terms of two bases. I can say log base 4 of 6 is the same as saying log of 6 divided by log of 4. Now this 4, if I want to go back to a single log, I can just bring that 4 simply back into this slot here, log base 4 of 6. That's the idea. Now there's an interesting way of showing this. Let's pretend I've got y is equal to e to the x, the natural exponential function. If I take a log of both sides, log of y is equal to log of e to the x, and then I want to get x by itself, let's see what happens. So x will go to the front. Now I've got x log e, and I want to get x by itself, so let's divide both sides by log e. So x is equal to log y over log e. Now our changing base rule means that I can bring that e here. So x is equal to log e of y. Now we know log base e, is the same as ln, so I can replace it like that. So x is equal to ln y. So we can see that relationship between the natural exponential function e and its natural logarithm. We can rewrite this as y is equal to e to the x can be exchanged with inputs and outputs, x is equal to ln y. Pretty cool. All right. Now, here is the changing base rule. It's really handy for your notes, and I think they've written it slightly differently in the book. Log base a of b can be also expressed as log b over log a, and these logs can be anything you want. So it can be 10, it could be 5, doesn't matter. The c's essentially cancel when we simplify again. That's a pretty interesting rule. We're going to use a changing base rule to solve some equations now. Okay, so here we go. Here's an example. I've got log base 5 of x take 2 plus log base 25 of 100 is equal to 1. Now this is not such a straightforward problem because you may note that we don't have the same base. I'm just going to scroll up again. Do you remember the solving logarithmic equation notes? Write all terms in log form with the same base. This is step 1 coming into play, and we can use the changing base rule to help us figure this out. So I noticed that 5 and 25 have a relationship, i.e. 5 squared is 25. I'm going to work at this log 25 here to see if I can express it as a log 5. To do that, I can go log 25 of 100, changing base rule, is exactly the same as saying log 100 divided by log 25. That might not seem that useful until we look at this step, and it's pretty cool. 25 becomes 5 squared, and then remember the third log law, the 2 can go here as a coefficient. Now what's really interesting is we have log 100 over log 5. Now that is a changing base rule, isn't it? If I have a log 100 over log 5, this 5 here can go back and become the base of this log. So therefore, we can now express this in terms of log 5. So you may note down here, I have a half log base 5 of 100. So now I'm going to bring everything else down because I haven't been touching this at all. So log base 5 x take 2 comes down. And I have changed 1 because now I know that the base I want to match up with is 5. So log base 5 of 5 to the 1 or just 5. Now I'm going to bring that half up and get rid of those coefficients. 100 to the half is 10. Remember it's the square root. Then I equate them together. So let's bring these together. 10 lots of x take 2 is equal to log base 5, 5. Then I equate them. 10x take 20 is equal to 5, solve, and x is 2.5. So that's the lesson. We've looked at some logarithms. We have a nice intuitive understanding now of how to think about logarithms through this example here. We've learned about the more advanced way to think about them. We can now evaluate logs of different bases. We've learnt the 3 log laws and how they work. We had a look at the natural logarithm and the natural exponential and how they're linked. And we've learnt how to simplify logarithms in terms of a single simplified logarithm. We've also learnt how to convert from exponential into log and log into exponential equations. We've also looked at the changing base rule and how it can be a really useful way of converting bases so that you can solve logarithmic equations. We also looked at some logarithmic equations without changing bases and the processes, the steps are involved in solving these. I hope you found this video useful. In the next video, we'll look at logarithmic functions and how they're related to exponential functions.